Using gas cylinders in urban homes is like living inside a bomb. Just look at this accident that happened in my country like a week ago. So I decided that as we also live in an urban home, why not I add a gas sensor to our kitchen? So I decided to look for the available gas alarms that are available in our marketplaces online. And then I looked at these available options. Most of them are either very weak ones, like it has like 590 taka, which is more less than like $5. And then we have the industrial ones like 26,000. 26,000 in my country it means about $200. So these are not actually viable options, so I decided to build one myself. Like ignore my desk, it's messy. So I have built this out of a plastic container because I had nothing uh, else that fits better than this one. I could print something with a 3D printer, but I didn't take any hassle because this might be a prototype. If people are interested, I'll build one more compact than this. As you can see, we can decrease the amount of space that's being wasted. So this has a OLED display, a RGB LED to show different states like a leakage state or other states like Wi-Fi or Bluetooth. This has Wi-Fi or Bluetooth because it's using ESP32. This has a microphone sensor so that when the device is idle, like no one is around, it can turn off the display, and someone comes inside the room or the kitchen, it can turn on the display. After 30 seconds it can turn off. This is because to save the this is to save the battery life in case this is running on backup, although this is actually designed to be run on the grid directly with a C-type port. And it has a MQ6 sensor, which is a okay, so it has a MQ6 sensor so that it can detect LPG, propane or butane. And this is a switch, and this is a buzzer, and the circuit itself. So I'm opening it up. I'll be pausing the video. This is the inside of this prototype device. I have a booster because the battery is actually 3.7 volt. I cannot run all the components like the MQ6. It runs on 5 volt, and the main brain of this project, which is the ESP32 WROM32 dev kit version 1. It's a microcontroller, very cheap one. I got it for like $2 or less, and it's soldered into a board. I have connected both of this board into this single board, prototyping board actually, and then I've connected all the sensors here. One of the biggest problem of this project was to measure the output of the sensors, because the sensors run on 5 volts directly from this booster, and then sends the data to the ESP32, which actually runs on 3.3 volt maximum. So the ADC pins, or the pins that are on the ESP32, can only get signals up to 3.3 volt, but my sensors like this MQ6 are sending signals way above the 3.3 when it is fully on, like it's sending up to 5 volts. So I had to use voltage dividers. Like I have added three 10k resistors, two in series and one in directly connected to the ground from the analog pin, so that I can divide the voltage, in this case roughly by 1/3, so that I can measure the voltage that is coming from the sensor through the ESP32. This is all. I have also connected this kind of voltage divider into directly into the cell of this battery, that is connected to this type C generic module. This is a very generic module. I've connected a voltage divider similar to this but with a higher resistance to the cell directly, so that I can measure the voltage of that cell, so that I can monitor the battery percentage. I can convert it to a battery percentage. from this analog signal to this digital signal by converting it to digital signal with an ADC that is built into the ESP32. Then I have chosen a buzzer that has a signal pin. As you can see, it has 3 pins, one for the 5-volt input, one for the ground, and one for the signal. I chose this because the buzzer take inputs of 5 volts. If I had to run it directly from the ESP32, then I had to use a transistor so that I can switch with a slower signal like 3.3 volts to this input 5 volt. But I chose this signal one so that I can put any signal like above 1 volts and it can turn on fully. So that's why I chose a signaled one. And a microphone module. The microphone module also has, this is actually a directly digital module. I use this module because instead of measuring the analog signal, I can just simply trigger, and I can set the trigger amount by spinning this potentiometer. So I'll turn this device on, I'll put it back on, and then I'll turn the device on. Okay, way I have put it back on, and let's just turn this device on. Okay, as you can see, the OLED is showing that it's booting, and it has booted. So by default it's showing. Okay, so I've turned the device on. As you can see, it just turned off, and then I give it a clap, and that turned on again. So it's showing the battery percentage, the Bluetooth signal, because I have not connected any, I've not given any Wi-Fi credentials. It's not connected, and it has turned on the Bluetooth so that I can connect to the Bluetooth, and by Bluetooth serial I can send the SSID and the password of the Wi-Fi that I'm trying to connect. And if it is connected, it will send the data to a remote server, that is casbar.vercel.app, and it will monitor and capture all the data that is sent by this device. So as you can see, it has a API counter. It's going way high because it's not connected to the Wi-Fi currently, so it's saying that 99 plus, 99 second plus. And we have the ADC, means analog to digital signal converter. I just added that icon so that it looks cooler, you know. Let's hit it with a lighter. Okay, as you can see, the ADC is reading like, it read like more than 300, so it tripped after the 100 threshold limit that I set. So also the LED also light up. So I also have a touch button here. I have added a touch signal so that I can restart the device if I want to. Like if I hold, it will show restart, hold to restart, and after like 5 seconds it will tell me to release to restart. If I release now, it will just simply restart the device. This is in case if the device is stuck for some reason and it's giving a false alarm, you can simply restart it. So let's see the portal that I have created. For now it's just showing me the data. I'll add a nicer UI to it so it looks nicer and I can visit it from mobile, so it's responsive to, and it's mainly built for using directly from the grid by a USB Type-C adapter. Most importantly, the main thing that is important here than the market ones is the software that I have written for this device. I've written it in PlatformIO in C++, not in Arduino IDE directly. So this code is entirely non-blocking. So no matter what I wrote on whatever the operation is, nothing is blocking nothing. So nothing is blocking the other ones. So this is the actual brains of this entire stuff. Also, I am using the thread system that the ESP32 offers to run the network operations in a separate thread, as you might say, with the X task create function. So this runs the network call in a separate part of the system, so that this other components, like the most important one, the sensor, are not blocked by the network call, because the network calls might take some time. And this is the rest of the code. This code is not open source. If someone is interested in this video, let me know. I will give an overview of this code, how I integrated it, and I'll share the code on GitHub if I get response. Thank you very much. Peace.